Algebra 1 class, this is Miss Graham, and today I'm going to take you through Lesson 5.1, looking at relations and functions. We are now in Unit 2 of our entire textbook, so make sure you have that new unit out. This whole entire unit is called functions, so we know that we're going to be looking at the fundamentals here. Go ahead and pull out pages 65 through 70. Our learning targets for today are we are going to represent relations and functions using tables, diagrams, and graphs. Our second learning target is that we're going to identify relations that are functions. Let's go ahead and look at our picture below here. We're going to use this machine, aka our DVD vending machine, to answer the questions below. So this is similar to Redbox, where you can see you insert money and push the buttons below to figure out which movie that you would like. And at the bottom, you usually take out your DVDs from there. So let's look at question number 1. It says, what DVD would you receive if you inserted your money and pressed the following buttons? So which DVD would you get if you pressed A1? That's right, you would get The Hunger Sports. As you can see, some of these movies are a little bit knockoff of maybe some real life movies, So I'm going to go ahead and fill in The Hunger Sports. Let's keep looking at the questions below. So now it says, what if I pressed button C2? Which movie would I end up getting? Perfect. You would see it's The Light Night, and you can see it's in this spot here, whereas our other one, The Hunger Sports, was in the upper left-hand corner. Now, we were reading these by looking at the letter of choice on the left and then seeing which number it goes with right above it. So that's how we were able to figure out that The Light Night is going to be the movie we get for C2. So let's go ahead and write The Light Night. If we keep going, we can see it also asks us what would happen if we press the button B3. What movie would we get? Well, here we can see we have The Amazing Insect Man that we would get. So we're going to put that down for B3. The Amazing Insect Man. Let's keep going and look at number 2. It now says, assuming the machine were filled properly, describe what would happen if you pressed the same button twice. So thinking about this, if we pressed the same button twice, wouldn't we receive the same DVD twice? It's going to be 2 of the identical DVDs for those movies. So we're going to go ahead and write down our answer for that. We're going to say, you should receive 2 DVDs, and we're going to say of the same movie. Let's go ahead and go to the next page. So this type of situation that we have actually relates to math. We're going to see each time we press a button, an input, that's what we're going to call our buttons, our initial buttons that we're pressing. Those are the inputs. And then every time we do that, we receive a DVD. That's called our output. So there's an input, there's an output. The button's the input, the DVD's the output. So number 3 says, in the DVD vending machine situation, does every input have an output? So I want you to go ahead and look back at our picture from the previous page and think about, does every single button have a DVD that comes out? What do you think? Did you get to look back at button 1, B1 specifically, right? If we look at B1, we can see that, oh no, it says it's sold out, right? So we know button B1 does not have an output since it's sold out. So we're going to say, let's try again. We're going to say, no, button B1 doesn't have an output, and that's because it's sold out. The movie is sold out. Now, to keep looking at this for our next number question, it says number 4. Each combination of input and output can be expressed as a mapping. So that's another vocab word that we're going to be focusing on. A mapping. And it can be written like so. Input to output. Now, off to the left, it tells us a little bit more about what a mapping is in the margin. So it says a mapping is a visual representation of a relation in which an arrow associates each input with its output. We can see that here. Input, arrow, output. So for example, in our vending machine case, we know B2 is our input. Our output would be the amazing insect man. So question 4A says we're going to write each of the possible combinations of buttons pushed and DVDs received in the vending machine. We're going to write them as mappings. They did an example above for us, but we're still going to write this down for every single one of those. So I'm going to have you go ahead and pause the video right here. I'm going to have you go ahead and write down mappings for each of the buttons to which DVD occurs. All right, go ahead and check yours with mine. So for A1, we should have gotten the Hunger Sports. A2 is the Revengers. A3 is Battle Sales. We skip B1 because there's no output. B2 is the Amazing Insect Man, as well as B3. C1 is the Dependables, and C2 and C3 are mapped to the Light Knight. So who would have thought that renting a DVD from a vending machine would have related to math? Now, here's what we're going to do. We're going to go ahead and look at part B for number 4, and it wants us to now create a table to illustrate how the inputs and outputs of the vending machine are related. So here's my hint for you. Think about how you would separate the inputs from the outputs and put that in a table. It's not going to look too different from what we have above, but it's a different way to show this relationship. Go ahead and pause the video right here, and then we're going to come back and check our answer. All right, let's go ahead and check our answers. What I did was I made a column for the buttons on the left, I made a column on the right for the DVD title, and then I went ahead and put each of the buttons along with the DVD title. So looking at this, we can also tell a little bit better visually that there was no output for our B1 button. So if you didn't put it in there, that's okay, because I know we didn't put it in the mappings above, but that's also another way that we can show this. Let's go ahead and continue below. Here it says mappings that relate values from one set of numbers to another set of numbers can be written as ordered pairs. You've probably heard of that before, right? An ordered pair could be an input and an output. Or maybe some of you are already starting to think maybe it could be an X and a Y. Now, a relation is a set of multiple order pairs. So keep in mind, looking on the left side, we know an order pair, it shows the relationship between two elements, our input and our output. It's written in a specific order. So our input has to come first, then our output, just like X comes before Y. It's also written with parentheses notation and a comma separating the two values. Whereas a relation, right, looking at a relation, is information that can be represented by a set of ordered pairs. So relations can have a variety of representations, just as what we said. So we're going to consider the relation 1, 4, and we're going to continue on to the next page. So let's keep going. Starting here, we're looking at the relation 1, 4, 2, 3, and 6, 5. It's shown in a set of 3 ordered pairs. This relation can also be represented in the following ways. So let's look at our first way. We have a table. And as some of you may have seen before, right, we have x coordinates on the left side, y coordinates on the right side. We actually have a visual representation of a mapping where we can see all our x coordinates are in the oval on the left. They are mapped to our y coordinates in our oval on the right. So just like the table, this shows inputs and outputs. So x's and y's, inputs and outputs, even though it isn't specifically labeled in this mapping. Now our graph, that's our final way that we're going to talk about right now of how we can represent our x and y coordinates. You can see it's a coordinate plane. Our x values are on the bottom and our y values are on the left side. We can see how we can plot those points on a graph. So this is pretty cool to look at, those three ways. Now let's start looking at number 5. It says write the following numerical mappings as ordered pairs. They did the first one for you. So it had an input of 1, an output of -2, and we wrote it as an ordered pair of parentheses 1, comma, -2, close parentheses. Go ahead and pause the video and finish the last 3 there. All right, did you get them correct? Go ahead and check yours with mine. We should get 2, 1, 3, 4, and 4, 7. All right, let's keep going on. We're going to go ahead and look at number 6 right now. A vending machine at the Ocean Road and Air Show creates souvenir coins. You select a letter and a number, and the machine creates a souvenir coin with a particular vehicle imprinted on it. The graph shows the vending machine letter/number combinations for the different coins. So here's what we're going to do, and I'm going to have you practice this really on your own. You're going to stop the video, practice each of these pieces, and then check in with me. So for A, it wants you to make a table showing each coin's letter/number combination. This is the one question that's probably going to have a little bit of variability to it. But just think about how you want to sort maybe the 3 different ideas, the coin's letter, the coin's number, as well as the type of vehicle. So think about how you want to sort that. I'm going to pause the video right now. Go ahead and do that, and then unpause to check. All right, go ahead and look in the margin. I made my table. I decided to have the leftmost column be all my vehicles. My middle column I decided to be the letters. And my right column I decided to have as the numbers. Really the way that I organized it was I decided to do the middle column first, the letters. I just wanted an A, B, C, D, E order. Now yours could look a little bit different. Maybe you alphabetized and did the order of the vehicles, or maybe you put them in number order, or maybe there was some other way that you did it. Either way, you're showing in a table how each vehicle is resulting from the letter number combination. Let's look at what part B is asking us now. Part B says write the letter/number combinations as a set of ordered pairs. Okay. This one's going to be maybe a little bit tricky because I'm also going to say, remember, it's not just each of the ordered pairs. Figure out how you can write the sets of them all together. Figure out how you show that relation. Pause the video right now and then go ahead and check your answer after. All right, let's look at what I wrote down. You can see that I didn't really need to know what the vehicle was. All I'm doing is putting the letter-number combination. So here we can see we have A5. They're separated with a comma and they have parentheses. I do the same with B2, C4, D1, and E3. A couple of things to notice is that I incorporated another set of really fancier parentheses. It's brackets. I put it on the outside of this to show that we are looking at all of these ordered pairs together. So make sure you add that to your answer. Something else that's also good to keep in mind is that the order of these points doesn't matter. So the order of each ordered pair doesn't matter. Obviously, we need to have our input first, then our output. But let's say I wanted to write down C4 first. I could totally do that. I could also write down D1 first. Maybe I want to put B2 last. That's what I mean by the order of each ordered pair doesn't matter. Ugh, that's kind of a tongue twister we're working with. All right, let's look at part C. It now says write the letter/number combinations in a mapping diagram. Ooh, you definitely got this. You got this. Okay, go ahead, pause the video here, see if you can do a mapping of our letter-number combinations. All right, let's go ahead and check our answer. We can see on the left side we have our letters. We can see on the right side we have our numbers. And we can see that our inputs have an arrow that goes to our outputs. And what we're going to learn later on is that each input only has one output. That's what we can see right here. Now, that's not always going to be the case, and we're going to relate that idea to what it means to be a function. All right, nice job practicing this problem, working through and seeing, okay, how can I visually represent ordered pairs? Or specifically, multiple ordered pairs for a relation. If we turn to the next page, we're now learning a new definition that's going to go along with what we said. A function is a relation in which each input is paired with exactly one output. So what I was bringing up before, that's what we're going to look at. Now, number 7 is going to have us refer back to the DVD vending machine problem. So it wants us to compare and contrast the DVD vending machine with the idea of a function. So I want you to say, do we think maybe some buttons in DVDs would be a function? Do we think some wouldn't? Go ahead and pause the video right here and see what you can kind of come up with. Well, we know with this lesson we're trying to relate math to everyday real life situations. So there is probably going to be some type of connection, right? We know the vending machine, it resembles a function because each input, the button pressed, has at most one output. Remember, if you press a button, 2 DVDs don't come out. You would have to press the button twice or 2 buttons. So answers can vary, but we're going to say this. We're going to say the vending machine resembles a function because each input, and in parentheses I'll put what that is. That's our button pressed. So each input has at most, that means no more than, at most one output, which remember, that is a DVD. So that's what a function is, where each and every input has exactly one output. No more at all. So let's go ahead and read question number 8. It says, suppose when pressing button C1 on the vending machine, both the dependables and the light night come out. It says, describe how this vending machine resembles or does not resemble a function. Okay, I gave you a little bit of hint before on number 7. Go ahead and see if you can answer this problem. Pause the video and we're going to come back and talk about it. All right, let's go ahead and read what I wrote down. I said such a vending machine would not resemble a function because one input, C1, yields 2 different outputs, the dependables and the light night. Here we know a function cannot have an input with more than one corresponding, which means matching, more than one matching output. We're going to do example 9 together. Example 9 says, imagine a machine where you input an age and the machine gives you the name of anyone who is that age. Compare and contrast this machine with a function. It says explain by using examples and create a representation of the situation. So thinking about this, maybe we could create the visual first. So what I am going to do is I'm going to show this through a mapping diagram. So I'm going to use a mapping to help me out with this. So let's say we're going to write down the different ages of students in high school. Well, we know high schoolers could be 13, 14, 15, and let's stop there because I think that's the age of most of you all. Now we have this in our oval. Now we have to map it to different students. So let's say we have a student, his name's Bobby, all right? Let's say he's 13 years old. That works because Bobby can't be multiple ages at the same time. Let's say we have another student, Megan, and let's say she is 14. We can map her age to there. Let's say we have another student named Liam, and let's say he's 15. We can go ahead and map his age there. Now, what if I put Anna on the list and I learned she's 13 as well? Well, oh boy, that means 13 is getting mapped to Anna. Oh boy, is this a function? Does every input just have one output? No. Well, what if I added Zach and he was 15? Oh boy, now 15 has more than one output. Oh boy, so starting to look at this, right? We started to look at this and saw, okay, our inputs initially had one output, but then when we added more students' names to the list, right? We realized that this would not be a function. So is this a function? We would say no, it's not. Ready? We know each input can be paired with multiple outputs. We know this because there are many people who are the same age. We're going to go ahead and skip number 10 right now, and you're going to go ahead and turn to the next page. We're going to look at problems 11 and 12. Looking at problem 11, it says determine whether the ordered pairs and equations represent functions. Explain your answers. So I'm going to do the first one with you and then have you do a little bit of the next two, and then we'll check in here. So looking at A, I want to make sure that every x value only has one y value. So looking at this problem, 5 only has 4 as an output. 6 only has 3 as an output. And 7 only has 2 as an output. We can see all of those, every x has its own unique y. Every input is matched with exactly one output. So here we would say yes, and our reason would be every input is matched with exactly one output. So I want you to go ahead and try parts B and C right now. All right, let's check our answers. Let's look at part B. I end up getting no. If you see the input of 4, you can see that there are 2 different outputs. We can see it gives us 5 and it also gives us 3. So no, that wouldn't be a function since our input of 4 can have an output of either 5 or 3. Now part C, I got yes, it is a function since every input is matched with exactly one output. Now we're going to look at part D and think about this from a linear equation sense. So it gives us the linear equation y equals 3x minus 5, where x represents input values and y represents output values. So think back to your math class last year. Think of what this would look like on a graph. Do you think it would represent a function? Well, maybe what we could actually do is graph it and have a better idea of what that looks like. Fortunately, we have graph paper on the right side, so what I'm going to do is I'm going to create a graph. And strategically speaking, I am definitely going to make sure that my y-intercept, my -5, I want to make sure I have that on the graph. So I want to make sure that I go all the way down to where it says -5. So I'm going to extend this a little bit. All right, perfect. And I'm going to treat each of these lines like it's worth one value. So to go to -5, to start plotting, I would go 1, 2, 3, 4, 5 down here. That's where I would start. And my slope is 3. That means I rise 3, go to the left. Sorry, rise 3, go to the right 1. So I go up 1, 2, 3 to the right 1. I go up 1, 2, 3 to the right 1. I go up 1, 2, 3 to the right 1. We know that we would then connect these points together. So visually looking at this, similar to the graph that we saw on one of the previous pages, maybe you want to refer back to it. We saw it on page 67. We saw that each of the x values has its own y value, right? In order to graph the points, right, we have to look at our x-axis first. We find out what the x value is. Like if I wanted to graph that point, that's going to be 1. And 1 as my x value, as my input, is always going to have an output of -2. So looking at this problem, seeing the straight line graphed, we can see, yes, every value of x will result in exactly one value of y. So really here, we can put the exact same answer as what we have in C. Now let's look at part E. Now we've changed up our linear equation. We now have y equals -x plus 4, where x represents input values and y represents output values. Really, the only things to change are our y-intercept, so where we're starting on the y-axis, and our slope. It's now negative. So looking at this, all we're saying is if we had a graph like this, and we had some type of negative slope, is this still a function? Yes, we can see every value of x. It will result in exactly one value for y. So really the answer that we had for C and for A, we're also having it for D and E. All right, we're on the last pieces. All right, we're going to look at 12, 13, and 14, and then we will be done. Woo! All right, so 12. It wants us to use positive integers to write two relations as a list of ordered pairs below, one that is a function and one that is not a function. So we know for this, if it's a function, right, we just have to make sure that our x-coordinate, each one has its own unique y-coordinate. Our inputs have their own outputs. Answers can vary, but let's say I write down the points, the ordered pairs, 3, 5, 5, 8, and 1, 9. Don't get tricked on these 5s because one is in our input spot, one's in our output spot. I also want to make sure I put brackets on both sides, but that would be an example of a function. Another possible answer is something you came up with as long as it follows those rules. Now, not a function. Like I said, our answers are going to vary, but I want to pick something where my input has multiple outputs. So let's say I did the point or the ordered pair 3, 5, and then I did the ordered pair 3, 8. I can see that each input has two different outputs. The input of 3 has the output of 5 and 8. And then let's put another random point. Now, something that is good to bring up, because I forgot this in the problem above, is for the function, we have to make sure we separate each of those ordered pairs with commas. So not only is there a comma in the ordered pair, it's used to separate each of them as well. All right, two more, and then we are good to go. So let's look at 13. This should be easy. Does the mapping shown below represent a function? Explain. Well, yes, it is. Look at this. Every single input is matched with exactly one output. This sounds really familiar. Didn't we say something like that up here? I'm going to highlight it up here. Didn't we say, yes, every input is a match exactly with one output? Guess what? We are going to take that idea and we are also going to bring it down to here for number 13. Exact same explanation. Now let's look at 14. It's a little bit of a different graph. So look at it, see if it visually represents a function. Well, let's say I try to go to the input or x value of 2. Look at how many outputs there are. There's an output of 3 and there's an output of 5. So no, this would not be a function because the input value of 2 has more than one output. Woo! And we are done. If your teacher has given you homework, go ahead and check your calendar and see what that is for tonight. Miss Graham's class, go ahead and turn to the next page, page 70. So for Miss Graham's class, your homework tonight is going to be numbers 15, 16, 17, 18. So all 4 of those problems on page 70. All right, have fun mathing.